Hey folks, welcome back. This will be the third video of the series section. By the time we're done this video, hopefully we'll have enough of an understanding to attempt the assignment. I think it's question 4 on the assignment, talks about converging and diverging. So if anyone has any questions after the 3 videos, feel free to reach out. I'm not guaranteeing I'll be able to get back to you. I'm on primary child care duty during the week, so I have a hard time getting back to you guys. But just remember, we do have our live kind of Q&A session. So if I don't get back to your questions between now and then, just make sure that you're keeping them in mind and asking them on that day. Because if you have a question, odds are someone else has the same question, and I'd rather answer them all at the same time. Okay, so let's take a look. We have talked about summing the first n terms in a sequence, or in other words, we've talked about series already. So we've talked about arithmetic series, geometric series. However, what would happen if I asked you to sum all of the terms in a sequence? So instead of saying finding S5 or S8, right, the first 5 terms, or the first 8 terms, how would we find the sum of all terms in a series? Or, in other words, what happens when n approaches infinity? So, this brings us to this idea of limits. A limit enables us to evaluate what happens to a function when the variable in the function approaches some value a. And the reason limits are useful, first off, they're the basis of calculus. With calculus, what ends up happening is that a limit can give us a good approximation, and then what calculus does is it takes those limits and makes them more and more specific until we get to an actual answer. But what a limit is it tells us what happens to a function as it approaches a certain value. So, for example, if I had the graph of some function that looked like this, where there's some asymptote here that the function actually never passes through. It never gets to that point. It just gets closer and closer and closer and closer. But what we see is that there looks like there's a pattern here where as the value, or as this function gets closer and closer and closer to that point, the answer goes up and up and up and up, and we can assume that the limit as it approaches this point would be infinity. The way that we write limits would be this. The limit as n approaches a for some function t of n. Now, in this case, a, where we're talking about all the functions or all the terms in our series, in this case, a would be infinity. So it's the limit as n approaches infinity of t of n. So, for example, how would we find the infinite term of this sequence? So let's take a look here. We're going to take limits of sequences as n approaches infinity. So the first thing we want to consider when we're trying to deal with something like this is we want to know the general term, right? If we know the general term, then it would just be a matter of plugging in infinity for n and figuring out what the value of that term is going to be. So here, what is t of n? Or in other words, what is the general term? Well, let's think about this for a second. What type of sequence is this? Is it arithmetic, is it geometric, or is it something else? And in this case, it's something else. So we would need to figure out a formula to help us figure out, or an equation to help us figure out what Tn is. In this case, it would be 1, because all of these numerators are all 1, over n plus 1, where the first term is 1 over 2, the second term is 1 over 3, the third term is 1 over 4, and so on and so on and so on. So then, what is the limit as n approaches infinity? So what we can do with something like this is there's a couple of ways of dealing with this. And the first check we're going to make is, well, what happens if I just take infinity and I plug it in for n? So what I'm going to do here is I'm going to take my general term here, and we're going to plug in infinity for n. So 1 over infinity plus 1. Now, infinity is an interesting thing. It's not really a number. Infinity is a concept, so it doesn't quite follow the rules you would expect when we're talking about numbers, right? So, in other words, for example, infinity plus 1 is just equal to infinity. infinity times some constant k is equal to infinity, right? So here, this thing is 1 over infinity. Now, what is 1 over infinity? So again, what's happening here is I'm not looking for the answer 1 divided by infinity, because 1 divided by infinity doesn't have an answer. It's just some number that is so infinitely small. It's just infinitely small. But what we're looking at here is we're looking at the limit as n approaches infinity. So we're talking about the limit as n approaches infinity. This thing is equal to 0. Because the number gets so small that eventually it's just going to be equal to 0. So when we're looking at infinities that are approaching infinity, or in other words, when we have some limit where n approaches infinity of some function or some sequence Tn, there's a couple ways we can do this. We could divide all terms by the highest power of n. And what that'll do is it'll take a lot of the things in our sequence or in our function and turn them all into 0. We could directly substitute like we did in the previous example, or we could simplify. Sometimes when we simplify, things cancel out and it gets rid of that infinity for us. Okay, so let's take a look at a couple of examples. So again, what I would suggest you guys do is pause the video, try them, see if you can get to an answer, and then start the video back up once you're ready to see the answer. So again, what I would suggest when we're trying to find what is the limit as this sequence approaches infinity, write the general term. What is Tn? And it might be arithmetic, it might be geometric, it might be something else. So in this case, technically it is arithmetic, but that seems like a bit of overkill for a pretty simple question, right? If the first term is 1 and the second term is 2 and the third term is 3, that means the general term is just n. So now what I want to do is I want to find the limit as n approaches infinity for the function, sorry, shouldn't be an equal sign there, for the function n. And what that means, if I use direct substitution, is that this thing is equal to infinity. Right, so as this sequence goes on and on and on, forever and ever and ever, up to infinity, its value is also going to be infinity. Okay, so let's take a look at number 2 here. So again, if you guys want to pause it, restart it, right, the whole thing there. So again, let's start off by finding the general term. So the general term is going to be equal to... so again, let's look at the pattern here, right? The first term has 1 over 2, then 2 over 3, then 3 over 4. So the numerator is going up by 1, the denominator is going up by 1 each time. So right away I see that this is n over n plus 1. Now let's try to find the limit as n approaches infinity of this thing, n over n plus 1. Now, the issue here is that this would be equal to infinity over infinity, right? If we just did direct substitution. And there's a problem with that, because infinity over infinity does not have an answer. There's no nice, neat answer here. It's not like anything divided by itself is equal to 1, because again, infinity is not a number, it's a concept. So it doesn't follow all of these same rules that we would know for numbers. Now, let's think back for a second. There's other ways of dealing with this question. There's step 3 here, where we could try to simplify, and there's this one here where we divide all all terms by the highest power of n. So let's see what happens if I do that. So for example, if I take this thing here, and I take everything in my equation, and I divide it all by the highest power of n. So now I'm looking for the limit as n approaches infinity for n over n divided by n over n plus 1 over n. Okay, now let's go through and simplify everything. So again, it's the limit as n approaches infinity of n over n is 1, n over n is 1, and this thing is 1 over n. And what I've done by doing that is I've taken the multiple instances of n and I've gotten rid of them. And what that's done is it's taken this thing right here and made it 1 over n. So there's my only instance of n. So now if I use direct substitution, what I'm going to get is 1 over infinity. And we've already talked about a number over infinity. This thing is 0. So what that leaves me with is 1 over 1 plus 0, which is 1 over 1, and that is 1. So this thing gets closer and closer and closer to 1. Finally, let's take a look at this one here. So we have some series, and again, right, pause the video if you want to try it on your own, and then restart it once you're ready to see the answer. So Tn is going to be equal to what? Looks like it's 2. It's a geometric series, so let's do it that way. 2 times 1/2 to the n minus 1, right? Where 2 is our first term, 1/2 is my common ratio, and n minus 1 here. I could simplify this thing a little bit because this is 1/2 to the negative 1, right? Or we could flip this and say that this is 2. So this would be 2 times 2 to the 1 minus n, which is 2 to the 2 minus n. Alright, so there's my general term. So then what happens here is when I take the limit of this thing as n approaches infinity, so of 2 to the 2 minus n, right, I can use direct substitution here. I can plug my n value right in, so I get 2 to the power 2 minus infinity. And again, infinity being this thing that's infinitely large, so if I take the number 2 and I subtract infinity from it, what I get is I get negative infinity. Okay, so this is 1 over 2 to the power infinity, right? Because if I take my negative exponent here, right, it flips it, we get the reciprocal. And 2 to the infinity, so an infinite number of 2's being multiplied is going to give me infinity, so this thing becomes 1 over infinity, and again, that is 0. Okay? Now, you could probably follow the pattern with a lot of these, right? So like this one, it's going up by 1. So if it goes up by 1 an infinite number of times, eventually I'm just going to get to infinity, right? This one down here is getting smaller and smaller and smaller. In fact, it's cutting in half, and it's cutting in half, and it's cutting in half, and it's cutting in half, until eventually it cuts in half so many times, right, the value is so small that it's at 0. This one is a little less obvious, but what's happening here is it's 1/2 away from 1, and then it's a 1/3 away from 1, and then it's a 1/4 away from 1, and then it's a 1/5 away from 1, and a 1/6 away from 1, and so on and so on and so on, until it gets so close to 1 that eventually just becomes the number 1. So again, give this a try. See if you can't figure out what this one is supposed to be. Then once you're ready, start the video back up and take a look. Okay, so here's another limit equation. This one's a little bit weirder, right? There's a couple instances of x, but for this one, it's a matter of understanding what infinity is going to do, right? So for this one, the first step here is the limit as x approaches infinity for 6 plus -1 to the power infinity over infinity. I'm just going to do direct substitution. The reason I'm doing direct substitution is this, whatever this is. So this -1 to the power infinity is kind of interesting because infinity, again, is a it's a concept. It's not a number. It's not even. It's not odd. So -1 times -1 is +1. But then times the -1 would be -1, and then times the -1 would be +1, and so on and so on and so on, right? But since this number here is neither even nor odd, we won't know what the final answer to this exponent actually is. We don't know if it's going to be -1 or if it's going to be +1. But what we do know is that if we take -1 or +1 and we put it over infinity, we're going to get 0. So whether this is -1 or +1, this whole bracket here becomes 0, and what that means is my limit is equal to 6. Okay, so let's take a step back and go back to series, because what we're going to be doing is we're going to use these limits to help us derive a formula to find the sum of an infinite series. So recall that series is simply the sum of the first n terms in a sequence. So a series is starting with term 1 all the way up to term n of some sequence. Okay? We can form a new infinite sequence using the partial sums of the terms. If the sequence of partial sums converges then to a number s, then what we say is that... Okay, so let me explain this for a second. So we're talking about converging and diverging. So maybe you've heard these terms before, maybe you haven't, but what it means to converge is that your series, as you add the numbers and you add the numbers and you add the numbers, to converge, what that means is eventually the sum is working its way towards some value, right? But to diverge, what it means to diverge is that your sum is not working its way towards anything. What it's doing is it's always getting larger and larger and larger and larger, or it's always getting smaller and smaller and smaller and smaller. So what we can assume is that if this is happening, our series will diverge, and if you find that sum, it's just going to equal infinity or negative infinity. Okay? So what this is telling us to do is it's saying, well, let's look at the partial sums. So what I mean by partial sums, so if I have some sequence that starts off t1, and then the next term is t2, and then the next term is t3, and then the next term is t4, right? What we can do with that sequence, or what we can try to do with the series here to try to find the infinite sum is, well, let's take a look at what happens. So S1 is equal to term 1. And then sum 2, what that's telling us to do is it's telling us to sum the first two terms. And then S3 is telling us to sum the first three terms. And so on and so on and so on. And 3. And what the goal here is to see if we can discern some kind of pattern, some S value that this thing is approaching. And if that's the case, then what we can say is that this obviously converges on that value, and that will be the sum of our infinite series. Okay, so let's consider this sequence right here. And I really like this one for a really simple reason, and I'll show you guys why in a second. So let's take a look at it in terms of the partial sums, and then let's take a look at it in a more visual way, okay? So to determine whether the series converges, we have to make the sequence of partial sums. So what we're going to do is we're going to take a look at sum 1. So sum 1 is a half. Easy enough. Sum 2 is 1/2 plus 1/4. So if we add those up, we get 3/4. Right? Sum 3 is 1/2 plus 1/4 plus 1/8, and we get 7/8. Sum 4, we do the same thing, so we say 1/2 plus 1/4 plus 1/8 plus 1/16. Sorry, 1/16. And we get 15/16. And what you might be noticing right now is that there looks like there's a pattern. There looks like there's a value that this number approaches, but it doesn't quite get to. And what that means is that the infinite series, if we were to take every term in this sequence, right, will have an answer, right? It's going to have an answer because this series converges. Maybe you see what it converges towards, maybe you don't. But what I'll do is I'm going to give you a bit more of a visual representation of this example. So if you want to do it along with me, you're welcome to. But what I'd like you to do is grab a piece of paper, okay? Fold it in half, okay? And rip it. Right, rip it in half. Rip it into 2 pieces of paper. Okay? Here's term 1. There's my 1/2. Right? And then I'm going to take this piece of paper that I'm left with, and I'm going to fold it in half, and I'm going to rip it. There's term 2. There's my 1/4. Right? And then I'm going to take whatever I was left with here, and I'm going to fold it in half. Right? And I'm going to rip it. And there's my term 3. There's 1/8, right? And I'm going to do the same thing with this piece of paper. Fold it in half, and I'm going to rip it, right? There's my term 4, there's my 1/16th, and then I can keep going here, right? I can do this and rip this one in half, and there's my 1/32, and so on and so on and so on. And what you'll notice is that as I keep doing this, if I were to take my terms, so my term 1 and my term 2 and my term 3 and my term 4 and my term 5, and I keep adding them up, eventually what I'm going to find is I'm just going to have that entire sheet of paper that I started with together as the sum of all of my terms. So what that means is that this series, the infinite sum of this series, is actually just equal to 1. The other way of looking at this is, how far away is this from 1? Right? It's a half away from 1. This is a quarter away from 1. This is an eighth away from 1. This is a 16th away from 1. So we can probably assume that the next one is going to be 31/32, and then the next one is going to be 63/64, where these terms are getting closer and closer and closer and closer to the number 1, never quite getting there. But if we're looking at the infinite series, right, again with this idea of limits where we're looking at a pattern as to what it approaches, what we can say is that, yeah, eventually this thing will just be 1. Okay, so thus to determine if any series converges, we simply evaluate t of n as n approaches infinity. So what that means is the t of n value goes to infinity, then the series diverges. Okay, so I talked about that a little bit earlier. So if your sum, as you're dealing with your series, if your sum, your s infinity, has some answer, right, that means this thing is going to converge. If your sum of the infinite terms of the series has an answer that's either infinity or negative infinity, that means our series diverges. So for example, let's take a look at this one here, where we have an arithmetic series that will either converge or diverge. So let's see what's going to happen. So let's see if this thing is going to converge, and if it does converge, let's find the sum. So let's take a look at my partial sums again. So my sum 1 is equal to 1. My sum 2 is equal to 1 plus 3, which is 4. My sum 3 is equal to 1 plus 3 plus 5, which is 9. And my sum 4 is equal to 1 plus 3 plus 5 plus 7, which is 16. Now, there's an interesting pattern here. Perfect square, perfect square, perfect square, perfect square. Right? It's something that's kind of neat that stands out, but is there some value that it looks like these sums are working towards? Some very clear number. Like with the previous example, right, these numbers were very clearly getting closer and closer and closer to 1. With this one, is there some number that these are getting closer and closer and closer to? And the answer to that is no, right? The numbers just keep going up and up and up and up and up. So what we would say is that this series diverges, right? It does not converge, it's going to diverge. And in fact, in general, all arithmetic series diverge. Because if you think about it for a second, if I'm just adding over and over and over and over and over again, if I add enough, my series is either going to be infinitely large or infinitely small. It doesn't matter how small the thing is that I'm adding. If I'm adding it an infinite number of times, it's going to diverge. Okay, so here's another one. Here's a geometric series, right? So let's see if this thing converges or diverges. So again, let's take a look at the partial sum here. So my sum 1 is equal to 1/3, and my sum of the two first terms is equal to 1/3 plus 1/9, which is 4/9, and my sum of the first three terms is equal to 1/3 plus 1/9 plus 1/27, which is equal to 13/27. So that should be a 7, sorry. And my fourth, the sum of the first four terms, so is equal to 1/3 plus 1/9 plus 1/27 plus 1/81, which is 40/81. And again, what we see here is that there looks to be a pattern, right? There looks to be something that we're approaching, but we're never quite getting to. And if you see the pattern here, the sum of the first infinite terms here is, so we would say, that this series, it does in fact converge. And the answer here is 1 half. So the sum of the series here for all infinite terms of this sequence would be 1 half, right? So here 1.5 over 3, 4.5 over 9, 13.5 over 7, 40.5 over 81. We're always off by just a bit, but we're getting closer and closer and closer to that 1 half that we're looking for. So what we can do now is we can take this idea of partial sums and we can find the what we can do now is we can take this and then take it one step further, right? We now, since the last video or 2 videos ago, we have a formula that describes arithmetic and geometric series. So what we can do now is, well, let's take this formula and let's see what happens as the limit of this formula as n approaches infinity, right? So what we can do is we can take our formulas for an arithmetic and a geometric series and we can take the n value and replace it with infinity and just kind of see what happens. So let's take infinity, plug it into my formula, and see what we get. So if I take my infinity here, 2a plus infinity minus 1 times d all over 2. Maybe some of you see it already, maybe you don't, but let's take a look at this and let's try to simplify this a little bit. So here infinity minus 1 is infinity. So 2a plus infinity d, right? Infinity times d is just infinity, right? So that means 2a plus infinity. Now, it doesn't matter what the value of a is here, right? A is going to be some number, and when I times it by 2 and then I add it to infinity, it's still going to give me infinity. Same thing with d. It doesn't matter what the value of d is here. If I take that number and I times it by infinity, it's still going to give me infinity. So what ends up happening here is this entire bracket turns into infinity. So I have infinity multiplied by infinity divided by 2. So infinity times infinity is still infinity. Infinity divided by 2 is still just infinity. Okay? So what that means is that if I take an arithmetic sequence and I look for the infinite term, what ends up happening is that my sequence will diverge, right? It's not going to have an answer. It's going to approach infinity. And the same thing is true for it could be infinity. It could also be negative infinity, right? I guess that's why d matters. If d were a negative number, then this would in fact be negative infinity, and that would take us down towards negative infinity. So it does matter in the sense that whether d is positive or negative, but it doesn't matter its magnitude. It doesn't matter how much it is, because when you multiply it by infinity, you're still going to get infinity. Okay? So any arithmetic series, any arithmetic series will diverge, right? They're always going to diverge. There's never going to be some answer to it. It's going to approach infinity or negative infinity. Now, an geometric series, on the other hand, is a little different. So again, let's do the same thing. Let's take this formula that we established in the last video, and let's take the limit as n approaches infinity. So when I do that, I do direct substitution. So I take that infinity and I plug it into my formula. So this thing is going to be equal to a times 1 minus r to the infinity over 1 minus r. Okay, so from here, it would seem like this thing also approaches infinity. But that's not necessarily the case. We have to think about this for a second. Will r to the power infinity, so will r to the power infinity always equal infinity? Right? We have to think about it. We have to kind of stop and be like, okay, well, is that the case? And it seems like it would. Right, it seems like it would. It seems like, okay, well, if r were, say, 2, well, we know 2 to the power infinity, yeah, that's going to be equal to infinity, right? If we know it was 5, yeah, well, 5 to the infinity, that's going to be equal to infinity, right? So we know that these numbers are going to be infinity. But are those the only values of r? Is r always these numbers? And the answer to that is no, right? We have seen some series that don't diverge, they do converge. So what's special about those r values that are going to make them converge in that case? And the answer to that question is r has to be between -1 and 1. It has to be less than 1 or greater than -1, but not equal to 0. So instead of doubling as our common ratio, maybe we're halving, or we're taking the third, right? And what happens there is that if I take 1/2 and put that to the power infinity, right, that's 1 over 2 to the infinity. And we know that 2 to the infinity is infinity, right? We already established that over here. So 1 over infinity is 0. So when this r value is a fraction between -1 and 1, right? When we put that to the power of infinity, it actually becomes 0. Oops. So therefore, any geometric series that has an r value between -1 and 1 converges according to this formula. So now, if this r value here, this exponent right here, that becomes 0, what is my new formula? A over 1 minus r. And let me just clarify something quickly. This might not look like the formula that we talked about the other day, or during the other video. I think the one during the other video was Sn is equal to A onto r to the n minus 1 over r minus 1. They are actually, these two things are actually the same formula, right? They are equal to each other. This is the negative of that, and this is the negative of that. And when you have a negative over a negative, it is a positive. So just quick clarification there. So this is the formula for an infinite geometric series when your r value is less than 1 and greater than -1. It's between 1 and -1. Right? So here's a couple of example questions that you might want to try. So give these a try. What I'd like you to do is, for the following sequences, determine if they converge, diverge, and if they do converge on some value, what is the value of the infinite sum? Okay, so take a look at these. Again, pause the video, start it when you're ready to answer, and let's take a look. So right here, right away, diverge. Right? There's no work involved. I don't need you to show me why it diverges unless it states otherwise. But how do I know this diverges? What type of sequence is this? It's arithmetic, right? So right away, I know if I'm taking the infinite series and an infinite sum of an arithmetic series, it's going to diverge. Okay? So what about this one? This is a geometric series where my r value is 1/2, right? So right there, it meets my criteria. It has as a geometric series that has an r value that's between -1 and 1. So now what I can do is I can use my formula. So the infinite sum of this series is going to be equal to my a value, right? So which is 1 over 1 minus r, which is 1/2. So 1 over 1/2 and 2. Right, so this series is going to converge, and this infinite sum is 2. Okay, do the same thing for the next one. So again, what type of series is this? Well, it's geometric, and my r value here is 1/3. So right away, what that tells me at this is going to converge. And it's going to converge on the value of, so again, the infinite sum is going to be equal to a over 1 minus r, which is 2 over 2/3, which is 3. Okay. All right, one more. So question 4 here, so 2, 4, 8, 16. So again, it's geometric, where my r value is 2. Doesn't meet both criteria, right? So this thing is going to diverge. Okay. All right. Try a couple more examples, and then we'll call it a night. So here's one where your series is given to you in sigma notation. Okay, but don't let that scare you, right? It's still a series this is geometric, right? Where your Tn is here, right? So this is your Tn, your general term that we should be used to, and that's fine. So what that means is that we know our term 1 is 0.2, and we know our r is 0.4, right? We know these values because we should be somewhat familiar with our general term, right? So our Tn is equal to term 1 times r to the n minus 1, right? So if I pick those values out from this formula here, right now it's just a matter of deciding, well, this thing is geometric, right? My r value is less than 1. All right, so then I can use my formula. So the infinite sum here is going to be a over 1 minus r. So 0.2 divided by 0.6, which is 1/3. Okay. Do the same thing for the next one down here. So again, it's a geometric series. Right here's my general term where my a value is 1.1, and I'm apologizing you guys getting confused. I'm kind of using them interchangeably. A and T1, right? Term 1 and A, it's the same thing. Sorry if that confused anybody. And my r value here is 1/3. So geometric series, r is less than 1. So let's find the infinite sum by using my formula. So 1.1 divided by 1 minus 1/3, which is 1.1 over 2/3, which is 3.3 over 2, or 33 over 20, or if you're more inclined to use decimals, 1.65. Okay. All right. Take a look at a couple more examples, and then we'll call it a day. So for these questions, what we're being asked to do is we're being asked to find the r value, right? So yeah, most of the time, what you'll be asked to do is determine whether it diverges or converges, and then if it does converge, find your infinite sum, right? Those are normally the questions you're going to be asked, but not to say those are the only questions you could be asked, right? If I give you the infinite sum, I might ask you to find, well, what was the starting term? Or I might ask you to find what was the common ratio. And it's just a matter of taking your formula and rearranging it, right? So if I take my formula, that is the infinite sum is going to be equal to a over 1 minus r. Well, let's take this formula here and plug in my known values. So 1/2 is going to be equal to 1/3 over 1 minus r. And then just solve for r. Okay, so rearrange my equation. I get 1/2 times 1 minus r is equal to 1/3. 1 minus r is equal to 2 over 3. Negative r is equal to negative 1/3. So then r is 1/3. Okay. Do the same thing with the next one here, right? Take the information that we're being provided and try and solve for r. So again, my infinite sum is 3. My a value is 1, so 1 minus r, right? Do some rearranging. So 3 onto 1 minus r is equal to 1. 1 minus r is equal to 1/3. Negative r is equal to negative 2 over 3. So then r is 2 over 3. Okay, so we'll call it there for the night. That's all I had planned. What I kind of expect from you guys going forward is take the next couple of days, attempt the assignment, attempt some of the worksheets, and then come to our live Q&A. I might be wrong. Correct me if I'm wrong. For this class is Wednesday at 7. I've got the other class is Thursday at 7, so I might be mixing the two up. But it's in the poll, so check it. So if you do have any questions, come that day prepared, and I'll come ready to answer them. The other thing is, if you can't make it that day, reach out, let me know. We can always schedule kind of a one-on-one meeting, or if there's multiple people that can't make it that day, maybe I'll schedule a second call that'll be a little bit quicker. I'll also record the call, so that way if anyone does miss it and they want to go back and listen to some of my answers, that'll be there as well. And what I think I'll do is I might have like a quiz or like a little test at the end of the week, or maybe early into next week, just to give you guys a chance. So we'll schedule that. I'll let you know well in advance when it'll be, and then I'll get you guys to try that, and then we'll kind of move on to the next unit. We're not going to be doing interleaving. I know that was something that was different, but I'm gonna go back. I'm gonna finish off trig next, and then I'm gonna go on to the next unit, and we're just gonna work our way completely through that unit, and then we'll go from there. All right. So I'll hopefully be seeing you guys on Wednesday. Have a great night.